So here we're going to look at writing the equation of a linear model through any 2 points. So given the situation of the number of border apprehensions, if you look at the year since 2000, 0 would represent the year 2000, 4 would represent the year 2004, 8 would be the year 2008, and so on. The number of apprehensions are in thousands, so that 1,643 does not mean 1,643. It means 1,643,000. So as far as what number that is, remember that just the 3 would represent 3,000. 43 would represent 43,000. And then 643 would represent 643,000. So that 1 would actually be in the millions place. So that first number really represents 1,643,000. The last number in the table, the 852, that would represent 852,000 apprehensions. So we have the scatter plot that goes along with it, and notice we use the year since 2000, and we have all the points plotted. And what we would have done in the past was we would have used the first and last points. And you did that in the last lesson. And if you look at drawing a line through those 2 points, that is not a good linear model because all the other points are well below that line. Now the reason that's happening is because the last point on the scatter plot, notice what happened is that increased. So it looks like there was a general decrease as time went on, and then in that last year, in 2019, the number of apprehensions jumped up to 852,000. So that point is a bit higher than what you would have expected to happen in the looking at the rest of the data. So that's the whole point of this lesson now, is that we're not looking at just using the first and last points. Now that we have the scatter plot, we can see that those first and last points are not the best points to use. So in number 1, we previously wrote a linear equation for the number of southwestern border apprehensions. We found the equation A equals 1,643 minus 42x by using those first and last points. So if I draw that model, again, this is not a good model, but I tell you to draw it. Okay, there it is right there. If we have 2 points, we can always write a linear model. However, it may not be a good linear model. So is that model we drew a good model, and why? Well, again, we already talked about this. The linear model that goes through the first and last points is well above all the other points, so that is not a good model. Okay, and then we're going to use the points 2004 and 2016 to create a better linear model. So if we look at which points they are, that's 2004. Okay, that's when x equals 4. And 2016, which is when x equals 16. Okay, so if we look at that, that's the second point on the scatter plot. And then the 16, 409, that's this point right here. Okay, so I'll just highlight those in red. Okay, so this point and this point. And we'll draw a linear model through those points. Now it looks like that will be a better linear model because we have a few points above that line and a few points below the line. And we could see that that line captures the general trend downward. All right, so our next goal is to write an equation for the linear model we drew from number 2. Our first equation used the first point in the data set. The advantage to that is that we know right away that the starting value is the vertical intercept, and that's 0, 1643. However, in number 2, we did not use that first point, so we cannot use 0, 1643 as the starting point. And this is the essential thing to understand in this lesson, is that we're not using what they gave us as the starting point. So by examining our model from number 2, is the starting value higher or lower than 1643? So looking at our scatter plot, 1643 is up here. Our linear model, the red one that I drew, it looks like it's lower. So if we were to guess, we might guess that that's right around 1400, because right here on this tick mark is 1000, and then 1500 is up here. So you might guess right around 1400. So we know it's lower, and we would guess about 1400. Okay, so moving along to the next page. So remember that a linear model always has the form output equals the starting value plus the slope times the input. And we've written several equations in the last lesson using that concept. The idea was, in the problem, we were given the starting value, and we either had to find the slope, we were given the slope, and then the input was your x variable. So we need to find the starting value and the slope of our linear model. All we know is that our linear model passes through the points 4, 1139, and 16, 409. That's all that we know about about our line so far. So far, our starting value is only a guess. So we guessed it was around 1400, but we don't know for sure. Therefore, our first step is to find the slope between our 2 points. So if we find the slope, or the average rate of change, between these 2 points, remember to find slope, that is how fast your output changes with respect to the input. In terms of this question, we're looking at how fast do the number of apprehensions change as the time goes on. So to find the slope, again, you can pause the video and try this, because you should be able to. So we find the rate of change, okay, which is 409 minus 1139. That's the change in the apprehensions divided by the change in the time that went by. So the slope is negative 61.8, or right about negative 62,000 per year. When it says round to the nearest 1,000 apprehensions, so 61.8 will round to negative 62. Okay, so it looks like the number of apprehensions decrease at a rate of 62,000 apprehensions per year. Going on to number 5. Now we can find the starting value of your model. We can use the slope we found and the fact that we know our line passes through the point 4, 1139. So substitute those values into our equation to find the starting value. So we know the number of apprehensions equals the starting value plus the slope times the input, the number of years since 2000. Well, we just found the slope up here to be about negative 62, so we'll use that. We know there were 1,139 apprehensions in 2004. So we're putting x equals 4 into our equation. Now notice, when we have that equation, the only thing we're missing now is the starting value. Okay, so if we go through and solve that, we do negative 62 times 4, and then add that to 1139, and you end up with 1387. So our equation, the number of apprehensions, started at 1387 and decreased by 62 thousand every year. Okay, so there's our equation. And again, what you want to notice here is that the starting value is 1387. That is what we would predict based on all of the other data points. So rather than using the first and second points, now that we're using the red line here, we guessed it with that starting point would have been about 1400. Now, in essence, what that's really telling us, without going into too much detail, is that it appears, based on the data, it appears that we would have expected fewer apprehensions than there actually were, because there were 1,643,000. We would have expected fewer than that based on the rest of the data. All right, so we have our equation. So to summarize what we just did, to write the equation of a line through 2 points, we find the slope, and then use the slope and one of the points to find the starting value. So that's the process we just did up top here. Next example, I give you just 2 generic points, 2, 9, and 4, 21. Write the equation line through those points. Now we don't have the starting value because we don't have 0, something. They don't give us that as one of the points. So we have to go through that same process we just did. Find the slope. Okay, in this case, the slope is 6. So the change in the y value is 21 minus 9. And then 4 minus 2. So basically saying the y value went up by 12 when the x value went up by 2. And 12 over 2 reduces to just 6, or 6 over 1. And I would always suggest you reduce the slope if you can. So we know the slope is 6. So now that we know that, we're going to take the idea of our starting value plus the slope times x equals our output. So you can use either point you want here. I used x equals 2 and y equals 9. You could also use 4 and 21 for your x, y values, and you'll get the same starting value, believe it or not. And you can go through and try that if you want. So 6 times 2 is 12. So you're going to subtract 12 from each side, and that ends up giving you -3 for the starting value. So it turns out that 0, -3 is our starting value. And if you just think really quickly on a graph, what's happening here is that we start with the point 2, 9. So 2, 9. Okay, so I'll take a point there. And then the other point is at 4, 21. So that's like this. So if we were to graph that line, now I missed it a little bit here, but the idea will be the same concept. So that line, where does it start at, meaning where is the x value equal to 0? That happens when y is -3. Okay, so again, the big concept here is to understand that the starting value is always the y-intercept, or when x equals 0. And they didn't give you 0 here for x, so you have to find that point. Okay, so moving along to the next example here. So same idea, except now just a different context. So I give you the average annual temperature at several different elevations in a region. So graph a linear model through the points 600, 19, and 2000, 5. So that first point, if you think about x, y, 600 is the elevation, and the y value, 19, is the mean annual temperature in degrees Celsius. So if you're at 600 meters elevation, you would expect the mean annual temperature to be 19 degrees Celsius. At 2,000 meters elevation, you would expect the temperature to be 5 degrees. And think about, if you think about what happens as you go higher in the atmosphere, the temperature decreases. So that kind of makes sense. Okay, so through those 2 points, you can draw the linear model. So 600, 19, that might be this point here. And then 2000, 5 would be this point here. So if we draw that linear model through those points, okay, so that looks like it captures the trend of what's happening. Now we might predict it based on that line. It looks like our starting value is going to be right around 25. So we'll see if that works out. So let's write the equation of our linear model. So again, we need to find the slope. So pause the video if you need to work on it. So we have the change in temperature over the change in elevation. A lot of students look at that and say, well, gee, that's a really weird number to get. But remember, the slope is always the change in the y value, which is temperature, divided by change in the x value, which is the elevation. Every single time, that's how you find rate of change. You take the y value over the change in the y values over the change in the x's. So that works out to about negative 0.01 degrees Celsius per meter. So we subtract the degrees Celsius on top, meters on the bottom, so those are our units. Okay, and then you take our starting value, which we don't know. We know that when you're at 2000 elevation, so when x is 2000, you're at a y value of 5 or 5 degrees Celsius. Plug in our slope, negative 0.01, and then do the arithmetic there. So 0.01 times 2000 is negative 20. Add that to each side and notice we get 25, which is what we thought it would be based on our model. We're close to 25. Okay, and then make sure we define our variables. We're letting T represent the temperature and M represent the elevation. So the temperature is starting at 25 and then decreasing by 0.01 degrees every meter. Okay, so to explain the meaning of the slope. Okay, and again, think about this, but instead of just watching this video and saying, oh yeah, I get it. That seems easy. It's easy when Marx does it. Okay, and then the vertical intercept is 0.25. So at an elevation of 0 meters, we predict a mean annual temperature of 25 degrees Celsius. And then use our model to predict the elevation when the mean temperature is 10 degrees. So we know that the y value is 10. So you solve our equation trying to find the elevation, m. And you end up with 1,500 meters. And then lastly, I'm not going to talk our way through these very much because we're running long on the video here. So they give you 2 years after she began her job, Janet paid $400 a month for her health insurance premium. And then 6 years after starting her job, she contributed $520 per month toward the premium. So write a linear equation for P, the monthly premium Janet pays X years since she started the job. So again, they didn't tell you when she started her job it was $400 a month. They're saying 2 years after she began. So what they're telling you there is a point 2,400, and 6 years after she started, that's 6,520. So they're giving you 2 points basically. So the process will be the same. Pause the video and try this, and I'll show you the answers. And then the last part. There. Okay, so pause the video if you need to spend longer.